Morning, everyone. So today we're officially starting into our new Chemistry 12 stuff. There are 5 big units in Chemistry 12. We're going to just take maybe 3 or 4 weeks going through each unit. Chapter 4 in particular for acid bases is a particularly long one, so we're going to actually break it up into 2 parts, but we'll get to that one when we get there. So starting off here, we're going to start off with unit number 1. Unit number 1 is a look at chemical reaction kinetics. So we're looking at the kinetics of a reaction. So basically it's the speed of a reaction. So reaction, we know we're dealing with chemical reactions. I'll just say RxN for short there. Kinetics here has to do with why are some reactions fast and why are some reactions slow? How can we actually measure this rate depending on the units that we have the rate expressed in? Can we actually bring about some of our stoichiometry to actually compare one chemical to another chemical? These concepts again. So starting off here, I'm going to introduce our main concept in this chapter, which is the notion of chemical rate. To actually get a rate, essentially what we want is to have a change in amount. You may remember from other science classes here, this symbol here, delta, is actually a shorthand for change in. Basically, you're tracking a change in amount, but the key hint here is it has to be a time rate of change, so it has to be divided by some measure of time. So, for example, a typical multiple choice question will be, which of the following units can be used for rate? They may give you, let's say, gram per minute, mole per liter, degrees Celsius per kilograms. Okay, so they give you all these units here. Now, we're going to talk in tomorrow's lesson here, what are some things that we can actually measure for the amount? We can track changes in mass, we can changes in pressure, changes in volume. There's a couple properties that we can talk about, but the key emphasis here is this bottom unit has to be some unit in time. Now the SI unit for time here should be seconds, but as long as it's any increment of time, we're fine. Grams per minute would work because minutes is a unit of time, while liters is not a unit of time, kilograms is not a unit of time, so therefore we have our option there. All right. So let's just start off with a quick reaction here. I'm going to take a piece of zinc. Zinc is a metal, so I expect it to come in a solid form here. I'm going to drop it into acid. It's a general property of metals and acids that basically we know it's going to be a single replacement, and basically the acids are going to start dissolving away at the zinc. It's going to single replace, and therefore we're going to get a combination between zinc and chlorine, and then we're going to get hydrogen by itself. Always do a double check here that you've written the formulas correctly. So for example, when hydrogen gets bumped up by itself, it actually appears as a diatomic, and it's also a gas, so hydrogen gas. Zinc is an alkaline earth metal, so +2. Chlorine has a -1, so ZnCl2. We make sure that our formulas are written correctly. I can check the solubility chart and actually verify that the zinc chloride is fully aqueous as well, fully dissolvable, no problem. And as a very last step, we do balancing just to make sure mass is conserved, just to make sure the recipe has the same number of each atom on both sides here. So what we're interested in here is we have a chemical reaction that's proposed to you there. You can watch it happen. So we have, let's say, here's my beaker. I first start off with some concentration of hydrochloric acid. It's currently fully aqueous. Hydrogen salts are going to be dissolved. And basically all you do is you just drop in a piece of mossy zinc. Basically, you're going to see in the container, it's going to start bubbling. That's an indication that the reactions are occurring. And actually in our reaction, those bubbles are actually expected to be bubbles of hydrogen gas. As that replacement reaction occurs, the zinc sort of breaks down and becomes Zn2+. That stays in solution, but it is the H2 gas that can actually leave the system. Depending on which exact reaction that we're looking at, when we're interested, how can I sort of monitor the rate? It's going to really depend on what chemicals are actually reacting here. In this case here, I've set this system up in what's called an open system. So system, I just remind you, system is the part that we study. So this is the reaction we study. And there's some sort of features of different systems here. Our first system here is called an open system. As the speaker looks, there's no lid on top of it. So especially for a reaction like this, which is expected to release one gas, hydrogen is just going to escape. Because there's no lid on top of it, that hydrogen is gone. So even though the equation itself has a balance ratio and all the elements are accounted for, I'm going to find that steadily this beaker here is going to slowly drop in mass as the hydrogen itself leaves. Everything else can't leave. The zinc as a solid is sitting there being eaten away. The HCl is fully dissolved. The ZnCl2 is fully dissolved. But that solution has to remain. The only thing that can leave is actually H2. So we refer to this as an open system. An open system is one in which matter and energy can escape. So there's no lid or anything, especially in this reaction. As the hydrogen leaves, I expect the mass to drop. This actually gives us a nice way to actually track the rate. Remember, for rate, we need a change in amount versus change in time. Well, what I can do is I can put this whole beaker on a scale. We know our scales measure things in grams. We may have 1 decimal scales, 2 decimal scales here. Be careful when I put on that scale there. Let's say, for argument's sake here, my scale starts off at 210.00, right? So now this is the mass of everything. This is the mass of the solid chunk that I put in, the acid, the beaker, and whatnot, and the hydrogen as it leaves. Maybe when I put it on, when I first drop it in at 0 seconds, my mass reads this. And what's going to happen is, as the bubbles form, as the hydrogen actually escapes the system, let's say in 10 seconds of time, let's say the mass here drops to, I don't know, 204.25. And then maybe in another 20 seconds here, at 20 seconds, maybe it drops to 199.76, right? And basically what's going to happen is I'm going to expect that this number is going to continuously change as the hydrogen gets lost. And actually I can track, well, basically the only reason why my mass is decreasing is actually due to mass of hydrogen loss. So mass change is due to hydrogen lost from the system. Because hydrogen is the only thing that can escape, any mass difference that I have here is actually going to be the mass of hydrogen. Now, this would totally be a different story if I had a closed system. If I just put a watch glass or something on top of it, I basically, yes, the reaction is supposed to release hydrogen, but if I just sort of seal that beaker and the hydrogen can't escape, in that case there, based on conservation mass, I would imagine as the reaction is occurring, this number wouldn't change. So because in this reaction here, I realize hydrogen is escaping, it is the only one gas that's escaping here, any change in mass here I'm going to track is actually going to be due to hydrogen. So let's actually calculate. So let's say I'm interested, what's the rate in between 0 and 10 seconds, right? So from what I've told you so far, a rate has to be a change in amount. You're measuring some physical property versus a change in time. This time, our change in amount is just a mass change, and specifically, this is mass of hydrogen. Again, the only reason why this number here would actually be dropping is because hydrogen is being released, and I'm just sampling it. I took a reading at 0 seconds when we started. This is called our initial time, or initial reading. I took another reading at 10 seconds. Steadily, I would imagine, between 0 and 10 seconds, the hydrogen was slowly bubbling off. It wasn't like 210 for 9 seconds, and then just suddenly in the last second it hits 204. I would imagine that's a very continuous change there. So let's just try to track this change here. Whenever we do change, we just do sort of final minus initial. This time I'm measuring mass. So what's the final mass minus what's the initial mass divided by what's the final time minus the initial time here. Now, I know that the change is going to be due to hydrogen, but you're going to see that what I put in is actually going to give you the mass of the whole system. So let's say the mass at 10 seconds, I gave you this 204.25. I just totally made up this number here. I'm going to minus off the 210.00 grams, right? So this is the mass of everything. This is the mass of the beaker plus the reactants plus everything. But this is assuming that some of the hydrogen has actually got lost. In this case here, when I do that difference, that actually is going to tell me how much was actually lost due to hydrogen. For the time, I kept things fairly simple. So my clock says 10 seconds later on. I'm going to minus off 0 seconds is when I started the clock. And we basically have, let's go 204.25 minus 210. So basically, I lose 5.75 grams in 10 seconds of time. And when I just divide that number over, 0.575 grams per second. Let's do a double check that this is a unit for rate. For a unit for rate here, we have to have a time unit on the bottom. Perfect. So this says, even though I only sampled it at 0 seconds and 10 seconds, it's like after every second, I actually drop by 0.575. And in fact, mathematically here, I should be putting a negative. That negative just means mass loss. And just in this case here, you can actually write in positive terms here, you can write in words. We are actually releasing, right? Hydrogen is actually getting released in the system, releasing hydrogen at a rate of positive 0.575 grams per second. So you're going to see we're going to be a little bit sloppy with positive negative. Yes, through a calculation, the negative just implies loss. Overall, this beaker here is losing mass, but the only reason why it's losing mass is because the hydrogen is actually being released. So whatever drop I see in mass, again, mathematically, there should be a negative in this case here. You can actually write in words. I can use the term release, and I can actually requote it as a positive term. They're going to refer to this rate as the rate at which the product gets formed. Right? That's how quickly the H2 is being made, or you can say this is the rate at which the reactants are also being decreased. We're going to see more so in tomorrow's lesson here. What's convenient about this case here is not only, mass is a really easy quantity to track, this quantity here is specific to one particular chemical. This rate here is attributed to directly hydrogen. And if later on I want you to play around with the units, I want you to re-express, well, how quickly does the zinc actually get used up? Because I have the rate expressed in one chemical, I can just use a little bit of stoichiometry. Well, the mole ratio is 1 to 1, and I can actually re-express that rate in terms of other chemicals as well. So before I show you a practice question for there, I'm going to try this rate here again for the second increment. Rate is something that may continuously change. That's actually an average rate we're going to see in a second here. Again, for the rate between 10 and 20 seconds, we're going to take, well, what's the mass at 20 seconds? 199.76 minus off the 204.25 divided by, well, my clock says 20 seconds, and I am going to minus off 10 seconds of time here. Again, I'm taking a 10-second increment. Again, as expected, we're losing mass. 199.76 minus 204.25. This gives you negative 4.49 in that same 10-second time span here, and therefore my rate again is negative 0.449. Make sure your final units represent the correct significant figures and also have the right units. And again, that negative just implies mass loss, or you can say this is the amount of hydrogen that gets produced, positive 0.449 grams per second. And you're actually going to find here, based on these numbers, although both of these rates can be referred to as an average rate over the first 10 seconds, the average rate over the next 10 seconds here, in fact, the next 10 seconds, the rate was actually slower. So we're actually going to go through this chapter here talking about what are the factors that actually affect rate. If we know that, we can then think about how I can actually change the rate and actually make things faster or slower in case the reaction was too slow. So let's take the second number. So I was given between 10 and 20 seconds, the average rate was a loss of 0.449. Again, this rate here is attributed due to hydrogen, right? Because specifically, it's only hydrogen that can actually leave. What I want you to do is just take the second number just for practice here. Can you express, I'm going to requote this number here. Can you express this 0.449 gram per second? You're going to notice I dropped the negative, but I'm going to say it in words here. Can you re-express the 0.449 grams per second production rate of hydrogen? Well, hydrogen is a product, so it's being produced, it's being formed, it's being created at a rate of 0.449. Can you re-express that positive number as a loss of zinc? Right, so jumping from one chemical over to another chemical, and I also want you to play around with some units here. I want to see if you can leave it for me moles per minute. Right. So what's important for you to recognize here is we already know what the rate is. I already know the speed. This is how quickly hydrogen is being used up. But because we have the rate as expressed for one particular chemical, I can actually use some stoichiometry here. The hydrogen and the zinc are linked in the equation by a 1-to-1 ratio here. I can re-express this very same number. If I drop in a piece of, let's say, 5 grams of zinc here, if I want to know how quickly that grams here drops away or how many moles of it drops away, I can just re-express this number in terms of zinc. I'm going to come up with a totally different number, but I'm still not changing the speed. I'm just changing the way it actually appears. So let's just try it here. So question mark moles per minute. I'm going to remind myself here, this is talking about zinc. Whenever you're stuck, you just want to start off with the number given. So currently I was given the average rate between 10 and 20 seconds, 0.449 grams. I'm going to remember, even though this was the mass of the total system that was lost, we know the mass drop is because of hydrogen. So this grams is already hydrogen that's being released. This grams here is for every second. So over 10 seconds, on average, I lose 0.449 for the 10 to 20 second time frame. Because we want to compare two different things in the chemical equation, I need to use the mole ratio. So I'm going to go 2 grams to 1 mole for hydrogen first. And then you can check the balance equation. For every 1 part hydrogen, there is 1 part zinc. This is just your plain old stoichiometry that we've been reviewing here. At that point there, I've actually re-expressed, now I don't have things in terms of hydrogen, now I have things in terms of zinc. And now one last conversion they want you to do is they want you to not just moles of zinc, they want you to actually do it in terms of minutes, because seconds on the bottom, I'm going to multiply by one last fraction, put seconds on top to cancel out, and we know that 60 seconds make up a minute. So it's the very same sort of unit conversion practice that we've been seeing here. Numbers on top you multiply, on the bottom you divide. Let's take that 0.449 times 60, divide the molar mass of the 2, and if I re-express this term here, I'm getting something like 13 moles of zinc per minute. That's how much zinc is actually being consumed. Again, in words, I use positive for the hydrogen that gets produced. This is how much gets formed. You could say mathematically, you could actually add a negative if you want. You can say, well, because zinc is actually being lost, zinc is actually a reactant. You can put a negative just to imply that loss, or you can just say in words, the loss of zinc is at a positive 13. So you can actually play around with this wording here so that you can avoid having to deal with negatives. You can just say in words, the rate of zinc consumption, how quickly is zinc being used up, is actually positive 13 moles per minute. So mathematically, yes, you can say negative, but you can just actually keep it positive and say, okay, I know it's a reactant, I know it gets used up. If I plotted this out on a graph for you, so let's just plot here. So I've given you the sample here. We're going to take the total mass of the system. So this is beaker and reactant and all that. We started off with, I think I gave you a number, 210. So I'm going to have marking for 210 somewhere. I have a marking 200, 190. I noticed that based on the data readings that I have, my mass never really drops past about 190 or so. So instead of actually starting your graph here from 0 and then scaling it evenly here, you can actually break the graph. You're allowed to break the graph if your data doesn't fall into that region. I know our data is stuck between the 210 and 190 region. I'm going to plot the mass against the time. So time as the reaction occurs, we did it from 0 seconds, let's do 10 seconds, let's do 20 seconds. Again, it has to be evenly spaced. And then let's just plot the numbers. So the total mass at the beginning, I have a coordinate 0 to 10. So I'm going to go x coordinate 0 to 10, fine. At 10 seconds, it's going to actually be 204.25. So at 10 seconds, let's find about where 204 is going to be, somewhere maybe there. And then at 210, I just told you 20 seconds, I just made up a number here, 199. Maybe it does something like this. All right. So I had decided to take a reading in 10-second increments. I took a reading initially. I took a reading at 10, took a reading at 20. Again, it's unlikely that the mass actually stayed 210, and then the very last split second, then it dropped to there. We would imagine that the drop is actually fairly steady. And in general, when you plotted these curves here, normally you will get sort of a shape like this. All right. I'm just going to extrapolate, just sort of following that trend there. And there we go. That's just tracking. This is actually the total mass. This one here eventually is actually going to settle off. What do you think this mass, when it levels off at, what does that represent? Right? In that case there, you have to imagine, well, I started off with my beaker. I had the HCl. Sure, I dropped in the solid piece of zinc, so that also increases the mass as well. As we've been looking at hydrogen escaping, the total mass is going to leave. It's going to start bubbling. It's an open system. It just sort of escapes. Eventually, let's say when the reaction stops, either I have no more zinc or there's not enough acid to actually react with the zinc here. Overall, my mass is still going to read something. This overall mass that we actually come up with, wherever it levels off, might actually be the mass of, well, I still have the beaker there. I still have the solution. I still have all the chemicals that are aqueous. It's just that I'm actually without the hydrogen. So don't expect this to necessarily hit 0, because it's not like the whole beaker disappears. But what we're doing is we're tracking a relative change in mass. And again, the change is due to hydrogen. I want to show you here graphically, we actually have an advantage already. I've only taken the reading 3 times, but graphically I've just let's track the pattern between 0 to 10, 0 to 20. At this point here, we can actually track 2 different kinds of rate. So far I've said here, rate should always be a change in amount, change in some physical property versus change in time. In our case, we're looking at a change in mass versus change in time. How would you get a change in mass in this graph here? Well, because mass here, it's in grams here, it's on the vertical axis. What if I took, let's say, the y-coordinate here and the y-coordinate here? Well, that would actually be the change in mass. Great, so that's the top. How would I get a change in time? Well, the change in time, well, I have time on the x-axis here. I'm going to take the x2 and the x1. I'm going to take this axis here. Oh, this side here is actually going to be delta t. What have I calculated for the graph if I now go, well, this one here is kind of like your rise. It's the up and down, and the other one is the run. In this case, you should be telling me from the math classes here, well, that's just actually calculating the slope. The slant of this curve here actually tells me how fast the reaction occurs. So the slope on this graph here is actually the rate. At this point here, what we've calculated is we just took a reading at 0 and 10. It's totally possible that maybe, let me just zoom in here, maybe your curve was actually more curved at the beginning. It's possible it could have done something like this. What I've done is I've sort of, yeah, I know initially the rate may have been a little bit steeper and then sort of levels off. The rate is constantly changing. The slant is constantly changing. What I've done is I've just actually calculated an average rate. I just put a point at the beginning. I knew at 0 seconds we were at 210. I knew at 10 seconds time we had to be at that 204 number. What I did is I actually almost connected the dots here. This line here is called the secant line here. That line there, so the slope of the secant is actually the average rate. And in this case, as I've labeled, this average rate between 0 and 10 seconds. Basically, what happens is, realistically, maybe at first your reaction was really, really fast. The slant was actually really steep. It's negative because I'm losing mass. Over the 10-second time, it's not a constant slope all the way through. It steadily slows down a little bit. But basically, I wasn't watching between 0 and 10 seconds. I just know you have to drop by about 6 grams. You have on average 10 seconds. At what constant slope could I have dropped at so I encountered the same mass decrease over the same time? That would be the slope of this line that I just drew there. So whenever you want to calculate an average rate, you're just going to connect the dots. In a similar fashion here, I connected the dots here. At 10 seconds, I know what the mass is. At 20 seconds, I know what the mass is. I connect the dots. Maybe it is following the graph, maybe it doesn't. I'm not sure. But basically, I just connect those and then calculate the slope. That's called the average rate because it averages over, yeah, at first we were really fast and the slowdown. It sort of gets rid of all that complexity. What's a little bit harder is, what if I ask you something like, can you tell me what's my rate at 5 seconds? So if on my curve here at 5 seconds, I'm right here. Well, you notice here, I only have one instant in time, right? I only have the 5 second. To calculate slope, at minimum, I need to do a formula like y2 minus y1, x2 minus x1. I need to actually have 2 coordinates. I can't calculate the slope of a single point. So what we're going to actually do here is to approximate how slanted are we at 5 seconds, what we're actually going to sketch in is a line called the tangent. So take out a ruler here. The tangent line here is basically going to be a straight line. And essentially my hope is when you zoom in really close to that 5 second time interval, I'm hoping no matter what the curve itself looks like, I'm hoping my tangent essentially follows the curvature so that within a very narrow region of that 5 second time interval, basically my curve overlaps with your tangent. Notice that this tangent here doesn't change in slant. What you're going to do then is you're going to take any 2 points that are easy to read. Maybe I know that point there, 5 and 205. Maybe, I'll read this point here. Maybe this is 18 and 0. Take any 2 points on the tangent. If you find the slope of the tangent, that is actually going to be the instantaneous rate at this 5 second time interval. So I'm going to just make that note here. In this case here, if I find the slope of the tangent, this straight line fit that follows the curve, the slope of the tangent is called the instantaneous rate. It's the rate at a particular instant, instantaneous rate, and I've done it currently at 5 seconds. And what you're going to find is if you plot it out here, depending on how you eyeball your tangent, you might get a slightly different slope than the person next to you. That's totally fine. But basically, you see that instantaneous slope here is actually different from the average slope. The average is a lot more shallow, whereas the instantaneous at 5 seconds was actually quite a bit faster. Then it levels off to even slower than the average rate there. But there's the difference between average and instantaneous. Average, you connect the dots for the secant. Instantaneous, you have to draw the tangent. So we'll pick it up from there on tomorrow's lesson. Thanks, guys.